Salut tuturor, hi everybody. Avem și colegi care nu sunt de origine română. English or Romanian? In English, right? Okay. So, hi everybody. I will talk about an Android app which integrates a small language model. It's not deployed in the car yet. It's deployed in an emulated environment. It's what we call, it's in phase 2 of the app development. We plan a phase 3, which would implement or would port this emulated app onto actual hardware. And the hardware has just arrived today. I just picked it up from the person who delivered it to us. It will be located in Bucharest. We hope to have another piece of hardware also in Cluj at a later stage. So yeah, that's about it as an introduction. The agenda for today, why we did this project, a bit of a project overview, the 2 phases that I mentioned, what the goals we had in each phase, challenges that we faced, and what we learned and how we overcome the challenges, and if we will still have time and everything works well technically, with the setup demo. So, where do I point this? So why we did this? First of all, because we can. So to demonstrate our Android expertise. This topic that we worked on during this POC is a hot topic in the automotive industry lately, but all the OEMs currently are experimenting with cloud models, so connection directly to the cloud. The benefits of having a model in the car would be greater control over the model with increased privacy, increased security. Model is working even in remote areas where you don't have 5G or Wi-Fi coverage or 4G coverage. The biggest challenge compared to a cloud model would be the response time, right? Because in the car you don't have the computing power that you have in the cloud. So somehow you need to make it work fast enough and with enough quality that is comparable to a cloud version. Okay, we intend also to improve the driving experience. The idea would be that the driver has all the time with him or her an assistant that will instruct on how to do various things with the vehicle. And at a later stage, maybe we can even make it issue simple commands to the vehicle. So you give a voice command to it and, for example, it will turn on the lights of the vehicle, for example. Yeah, so let's let me see. Yeah, as I mentioned, the 2 phases of the project. So we had this project was started, I think, June this year. The first phase was in June this year. It was an exploratory phase where we actually had to select the technology, basically, and kind of define a path forward with respect to architecture. Second phase was using the lessons learned in the first phase. We refined the architecture. We let's say kind of finalize the technology choices, and we had the first application that is in a demoable state. It's not a perfect application. It's still slow, I would say. So response time is between 30 seconds and 1 minute, depending on the question. the target would be to decrease it down to 5 seconds or less. This is, I was telling to my colleague Anna that we just had a call today with one OEM that they are interested, and that's the target. We hope that by porting this into actual hardware, so not running in an emulated environment, situation will improve. And but compared to phase one, we had a performance improvement by a factor of 10 to 20, and I will mention this in my presentation. Yeah, so pretty much those are the two phases, and let's go a bit into each phase. As I said, phase one was an exploration phase. Here we had two goals. Actually, in each phase we had two goals. One goal was related to the so-called AI part or machine learning part, which is defining and implementing the RAG pipeline, the retrieval augmented generation pipeline. And the second part was related to the Android app itself, how it consumes the information from the pipeline. And how it interacts with the pipeline in general, so how it provides input to the pipeline and how it consumes the output of the pipeline. Biggest challenges in this phase with respect to the RAG pipeline was choosing the right programming language technology, choosing the right RAG libraries, creating the basic RAG pipeline, and pack the RAG pipeline in a way that is integratable with Android. What we learned is we explored several possibilities. Initial tests were done in a non-Android environment using Python and JavaScript. They were quite successful. The problem is JavaScript and Python are not natively supported in Android. For Python, you need to define some bridges, which can be quite complex from a programming perspective and introduce delays. For JavaScript, there is support, but we were not confident that we can have the same level of control over the operating system as we have with a native Java application, so we decided to go for Java. Luckily, the library that we choose for the RAG pipeline, which is called LangChain, had a Java variant, which at the time of the implementation was in the very early release stages, so it's version 0.31 that we used for this demo. I think now they are at 0.33 at least, I think. I didn't follow exactly the latest updates. Yeah. Why we choose LangChain is because it has built-in support for RAG. That means you don't have to write custom classes to have a functional RAG pipeline. We will see that in phase two, we concluded that probably customizing the existing code will be needed if we are to achieve this target of 5 seconds or less in response time. And also LangChain has a lot of configuration options that we need to explore. This was the conclusion in phase one. For example, because the model was improperly configured in phase one, the ingestion of the manual, so the reading of the manual by the model, took between 40 and 50 minutes on average, and the response time was around 10 minutes. Second phase, ingestion time is under 2 minutes, and response time is between 30 seconds and 60 seconds. So quite several orders of magnitude improvement, and mostly is because of the configuration, and there are some architectural improvements that I will mention. Okay, second goal was developing the first version of the Android app in phase one. Here we realized that LangChain 4J library has some, yeah, I cannot see the pointer, but has some incompatibilities with Android, because the PDF reading mechanism that was used to ingest the manual is relying on AWT library, which is incompatible with the graphical libraries and the graphical engine inside Android. And as a workaround to see something being ingested, we had to manually convert the PDF to a text file and ingest it as a text file. This led to suboptimal ingestion results, because due to Unicode translation and this kind of things, artifact characters were introduced in the text. Also, sentence beginnings and endings were not properly maintained. So the input to the embedding model was suboptimal, and thus also the input to the language model who was responding to the question was suboptimal, and in general the quality of the responses lacked because of this. Also, here the first architecture did everything inside the Android app. So both the ingestion of the manual and response to the questions. So everything was done inside Android, which also introduced additional delays. And we used a model that was originally connected to the cloud, right? So even with a model connected to the cloud, which was more powerful than the models we used in second phase, we had greater ingestion times and greater response times, right? And this was because of mostly of this problem with the quality of the inputs and how the whole thing was configured. Phase 2, same two goals, but here we try to find solutions to the problems we found during the exploration. First of all, we had to deal with the AWT dependencies. And the easiest way to do it, architecturally speaking, and this also helped parallelism in the application, was to run the model inside a Docker container which was outside of the Android environment. And the Android app would connect to the Docker container via HTTP request. So essentially, we had like a cloud running on a local computer, on a local machine. This maps very well to the architecture in the vehicle, where you have multiple computers connected via Ethernet. Some of them are running Linux, which can run Docker. Others run Android. And the idea is that you have your Android app communicating via REST APIs with another ECU. In one ECU, one hardware computing box, communicating via REST APIs with another hardware computing box that has Linux and hosts the Docker containers for the models and for the vector store holding the embeddings. That is the red PDF. Right? So essentially this architectural change eliminated both the AWT dependencies, so they took them out of the Android environment and increased speed. Yeah, also we did a bit of tweaking here. We improved the configurability of the pipeline in the sense that we added configuration parameters for the text segment length, text segment overlap, model temperature, model seed, number of segments that can be maximum number of segments that can be part of an answer, the matching. I don't remember now the name of the parameter. It's kind of like a matching probability. We set it to 60%, 0.6. That means the answers are less precise, so the model sometimes adorns or flourishes, like it gives a bit of context that's not in the manual, but this helps getting an answer faster, and also with a bit of a better quality, because if you're too precise and your segmentation parameters are not correctly chosen, the model tends to say that I don't know the answer, even if the answer is in the manual. Right? This is a very deep technical discussion. One of the improvements that we might do in the future with respect to segmentation would be that we will not segment at character levels, or like beginning and end of word level, but we will segment at sentence level, or phrase level, or topic level. But yeah, this is a separate discussion. Okay, so second goal was to integrate this whole thing that I described with the Android app. So essentially we had to rewrite the app that instead of invoking the LangChain library directly, it just invokes some REST APIs from the Docker images and essentially process the output. As I mentioned, we had a significant increase in performance. Future developments, potential developments that we consider are instead of using a naive, what's called a naive RAG pipeline that is built-in RAG functionality inside the library, we should create an advanced RAG pipeline in which the default classes are extended or overloaded with additional functionality, or even replaced with custom classes. You can see here that we'll do some pre-retrieval optimization and post-retrieval optimization. Pre-retrieval optimization is about speed and quality. Post-retrieval optimization is mostly about quality. Yeah, and as I mentioned, we plan to have the implementation in the car. And here, are we ready for a demo? Yeah. So let's try the demo. Just to set the correct expectations, be patient. This is a POC which was done, the model testing and configuration, and from software engineering and digitalization. Exactly. Thank you. Yeah, so that being said, written and audio form. And as a vector store, and to keep the hardware constraint of using maximum 1 GB of RAM, we, after several tests, we chose Tiny Llama or Tiny Dolphin as the models. Those are models with under 3 billion parameters. And in general, this type of models tend to consume, when run locally, under a gigabyte of RAM. So let's check that the Docker containers are running. You can see the vector store here running for some time now, and also the language, the embedding model and the language model container. And we will just start here some graphs so that you see what's happening when I ask a question. And here I have the Android app, and let me ask it a question. I will ask the question without this microphone because the echoes might affect the speech recognition, but the sound, I will use this microphone to play it back to you. Describe the air conditioning function. Describe the air conditioning function. It was started some time ago, and probably we will need to do some changes. Yeah. So let's briefly reset the microphone. Describe air conditioning function. Yeah, okay. So apparently the speech to text is not working as expected, but let's give it in text. So it can happen that if the emulator runs for a long time, and in this case I started 2 hours ago almost, if the computer goes into sleep mode and comes back again, something gets out of alignment, so to speak, and I need to restart everything. But to save some time, I can give it like that. And here we see the calculation has started. Also, we should see that the memory in the language model is going up, but not going above 1 gigabyte of memory. And after about a minute, we should see a response. But if let's say we will need to reset everything, then you're welcome during the networking to come by and I can show it to you.
So the demo was supposed to recognize your voice?
Yeah, but I think because the computer entered sleep, I need to reinitialize the environment.
Yeah, today everything is
So
not running. Preparing for vacation.
I did not anticipate this, yes. So probably I should have kept it connected to the power socket.
Okay. Okay, Tudor, let's take some questions then. No?
Yeah, please.
Vorbim în engleză. Any questions?
We have a response.
And an evaporator, which work together to remove heat from the air. When the engine is turned on, the compressor starts spinning, causing the refrigerant in the system to flow through the evaporator. As the refrigerant flows through the evaporator, it absorbs heat from the air and turns into a gas called carbon dioxide, CO2. The CO2 then rises up the evaporator, where it is cooled by the refrigerant. This process continues until the CO2 reaches a temperature of around 31 degrees Fahrenheit minus 0.6 degrees Celsius, at which point it starts to turn back into a gas called water, H2O. The water then flows through a condenser, where it absorbs heat from the air and turns into a liquid called water vapor, H2O. This process continues until the water vapor reaches a temperature of around 70 degrees Fahrenheit 21 degrees Celsius, at which point it starts to turn back into a gas called carbon dioxide. The CO2 then flows through a fan, which blows air over the interior of the car.
So some notes with respect to the demo from my side. Obviously, because it's a POC, we don't have very good error handling. So for example, you saw that if the system goes into sleep mode, there is no coming back from sleep kind of function. During sleep mode, the connection to Google services that do speech to text recognition is lost, and it's not reinitialized automatically when coming back from sleep. So I need to restart the emulator to make it happen again. Another problem that we have is that compared to a microphone in the vehicle where you have like hardware noise cancellation, here you don't have hardware noise cancellation on this microphone. And if there are echoes, it has problems recognizing what you're saying. You can write the software in a way that will compensate for that. It's not written like that. Yeah, pretty much that's it. And also what I mentioned, because the models that we used are trained on scientific data and on multiple languages, if the question is not specific enough, for example, describe the air conditioning function of the vehicle, it tends to tell you things also like how the whole cooling process takes place, right? Why this is happening is because of this parameter that I mentioned earlier, but also when we send the question to the model, we don't provide additional context to the model. So we can we send kind of like a story together with the question, and this is very brief currently, and we can improve this, tailor it to the need that we have here.
Okay, I think time's up.
Yeah.
Let's take some questions. So we got one here.
Does the model also take into account your past queries so that it
No.
runs?
No, I state this again, because this is a POC and it was done pretty much in between projects. It's not the production grade code or a production grade, or it doesn't have a production grade feature set, right? It's more like to illustrate that this is possible. It could have what you said, like a history, when we switch from a naive reg pipeline to this advanced reg pipelines. So this pre-filter and post-filter custom code will allow you to keep a buffer of previous messages and pass them on together with your latest question. This is what I mentioned about the story that we sent together with the question.
Thanks.
Yeah.
On which car? I mean, do you have any targeted car or not?
The manual you saw here was from Porsche Taycan.
Ah, okay.
Yeah,
And
but it can be applied to any manual. I mean, probably you can give it a book, like
but don't you depend on the hardware that's on that machine, like the ECUs and?
you depend only from computing power perspective, but that's it. And the target is to run with maximum 1 gigabyte of RAM. And here, in this example, we are running with 4 cores.
Ah, okay. Well, 4 core is
4 i5, like 2 physical i5 cores out of the 4 in the machine, 4 virtual cores.
Oh, okay. I don't know what. Okay. Any more questions? No.
Hi, Tudor.
Hey.
You've got a proof of concept running at the moment on a laptop. So is there any hardware acceleration that you're using?
No.
Here? Okay, and with the new hardware that you are looking to deploy to...
No hardware acceleration.
Right, okay. In terms of next steps of the proof of concept, you are going to deploy to a new platform, but what else are you hoping to do from a functional perspective with this?
That's a good point. So one improvement would be what the colleague mentioned, this having history of your conversation. Because it's not about just answering the latest question, it's about answering in the context of what happened previously, and is not just about sending the previous answers together with your latest question. It's about curating the narrative flow, like in the previous answers, which is it's a complex problem in itself from a an AI development perspective. Right, so the challenge here was not the Android app itself. The challenge here was more like understanding the AI technology, controlling it, and integrating it with Android. Obviously, we can improve also the Android app itself, like the way you interact with it. On the Android side, the way we do speech to text and text to speech can be improved. We used pretty much the basic, the default parameters offered by Google. And we need a network connection to the Google services so that this speech to text and text to speech to happen. But this can be eliminated in the future. Let's say Google offers the possibility to have the same functionality offline, but again, implementation complexity increases.
Okay. Okay, thank you, Tudor. Let's give him a round of applause.
Thank you.